Okay, this is going to be the first edition in my little study series for Math 214. I'll just put it out as a disclaimer. I'm learning with you. I'm not an instructor. So hopefully we'll both learn something from this. But I will be checking my answers and my work before I post these videos, so I'm not posting anything that's, incorrect or misleading. So this is a homogeneous differential equation that I found online, and today we're going to be going over the method in which we would solve this by using the Laplace transform method. In short, and we'll review this at the end, you take the Laplace transform of each term to convert this differential equation into a algebraic equation. From there, you will use partial fraction decomposition to find a series of constants. And once you have those, you can then apply those back to your algebraic equation and use the Laplace transform identities to go and find y of t. So we take the Laplace transform, we get our algebraic expression, we solve for our constants, and then we go back using the inverse Laplace transform. So without further ado, let's just get started here. Because of linearity, remember that like the Laplace transform of x plus y equals the Laplace transform of x plus the Laplace transform of y. And that, of course, also carries over to constants. So Laplace transform of x plus 2y would be Laplace transform of x plus 2, Laplace transform of x plus 2 times the Laplace transform of y. So we'll apply that here. We'll just write it out. The Laplace transform of y double prime minus the Laplace transform of y prime minus 2, and take out the constant, times the Laplace transform of just y. And then we do the Laplace transform on the right side. The Laplace transform of 0 is just 0. So we have nothing special there. Now we're going to look at the table. You can find this in Module 10 on Canvas. And notice down here, number 18, they have it as fn of t is equal to this bit here. And basically what this identity is it's saying that if you have some function or some equation f, in this case it's y, n is the order of the derivative, and t is the independent variable, then your transform will take on this this identity here. So let's write that out here. I'm going to write it in terms of y, so we're not having to mix variables. Y nth derivative of t equals s to the n minus s to the n minus 1 times y 0. And this goes on for, depending on what value of n you have, because you may have to have more and more terms. And then at the end, you will have minus y n minus 1 derivative of 0. So we're going to use this identity right here to solve each individual part of the left-hand side here. For this first one, we have y double prime, so n here is equal to 2. We'll have s squared. Ooh, I'm noticing I missed something here. See, I'm learning too. S of n is multiplied by y of s. So s squared times y of s minus s. This is going to be raised to the 2 minus 1. So that's 1. So that's just s times y of 0. And we'll go straight to the end. We don't have any more terms there. Minus y to the n minus 1. This is just denoting derivative. This is not actually an exponent, as opposed to the s's, which actually have exponents. So this is y prime, because 2 minus 1 is 1. And since we have y here, we're dealing with the function y. This is actually denoting a derivative, so y prime of 0. Okay, so this is the transform of this first term here. So what I'm going to do is I'm going to do it for this one, and I'll write out the whole Laplace transform. Okay, so this is everything written out. I want to add that we are defining y of s being the Laplace transform of y. So you'll notice here for the last term, minus 2 times the Laplace transform of y is just y of s. This right here is the relationship. So now we have this long expression right here. Well, we'll notice that we have our y0, y prime is 0. These correspond to our initial conditions up here. So we actually know what these values are given the initial value problem. So we can actually substitute those in. So anywhere where you see a y of 0 with being multiplied by something, that can cancel out. And anywhere where you see a y prime of 0, that goes to 0, so that will also cancel out. Okay, so having canceled out what we can, we now have this expression here, s squared times y of s minus s minus s times y of s minus 1 minus 2 times y of s. So you'll notice here everything now, almost everything has a y of s term. For the bits that don't, we can move those to the right side. We'll do plus s. This actually here should be a plus, so this would be minus 1. So these cancel out, and on the right hand side we have s minus 1. So s squared y of s minus s times y of s minus 2 times y of s equals s minus 1. And now you'll notice that every term on the left hand side has a y of s. So we can factor that out and reorganize this equation. I'm going to make some room here and I'll show you that. Okay, so now we have an expression for y of s. We factored it out of this, and we got this quadratic looking thing, and then we divided that on both sides, and now we have an expression for y of s is equal to s minus 1 over s squared minus s minus 2. So this is the point in which we would want to use partial fraction decomposition. We'll have to take it way, way back to high school algebra and figure out how to decompose this. So we're going to separate this denominator into factored terms. So you can go about doing that with either the old school factoring method or the quadratic formula, whatever. But once you do that, you'll find that this is going to equal s minus 1 over s minus 2 times s plus 1. Okay, so now we're set up for our partial fraction decomposition. So if you remember how partial fraction decomposition works, we have two terms in a denominator. We're going to set up our right-hand side here, select some constants or some variables, constants, whatever. We'll find that they're constants later. And then we take the first term here, s minus 2, and the second term, s plus 1. And now we can multiply both sides of this equation by the denominator. That'll cancel this out, and it will cancel out one of the terms. So we'll be left with s minus 1 equals a times s plus 1 plus b times s minus 2. So going from here, there's a few ways to go about this, but one of the ways that I like to do that seems kind of simple in a case like this is you have an s term and a 1, right? So you can sort of distribute these in your head and figure out what part of the right-hand side is going to equal up to the s terms and what part is going to equal up to the 1. So just to write this out in case that didn't make sense, the s term, you have an s on that side, is going to equal all the s terms on this side. So that's going to be as plus bs. So given that there's s's in every term, this can get factored out, and this becomes 1 equals a plus b. Now we have the second term, which is negative 1. So here we would have a minus 2b. That's that right there. So this is our second equation. So now we have these two equations and these two unknowns. So from this we can solve for a and b. So we're going to isolate a, and we'll find that a is equal to 1 minus b. We can take this and plug it into a, and we will find that b is equal to 2/3, and because a plus b equals 1, a must be equal to 1/3. Okay, so we found the values for a and b. Now let's recall what our partial fraction decomposition looked like before we jumbled it up. Okay, I know this is getting pretty long, but we are almost there. So this expression here, remember, this was equal to y of s. Let's go back to the table that shows all of our identities, and if you'll notice, look at the transformation, the s for row number 2 here. We're looking at this side because now we are doing the inverse. So we're going from this back to this in order to find y of t. 1 over s minus a. Well, that kind of looks like what we have in each of our terms here, both this one and this one, except for that the numerator is not a 1 in either of these. But remember, these numbers can actually just be coefficients that are taken out of the Laplace transform. So I'm going to write out that the Laplace transform of e to the at, this is coming straight from line 2 of the Laplace transforms table, is equal to 1 over s minus a. Okay, so for the first term, we're going to have a coefficient of 1/3 pulled out, and then it's going to be, this would now be 1 over s minus 2. So a here is 2, so this is going to be e to the 2t. Okay, now, again, because of linearity, we can just add and move on to the second term. Our coefficient here will be 2/3, and the same story. So e to the a here is 1. And if you'll notice, I made a mistake there. This is not the same operation, obviously. So this is actually s minus -1. So a here actually equals -1. So that is a negative t. So finally, after all those steps, this is our final value for y of t. Go over the steps real quick. Took the Laplace transform of each individual part. Then we applied our initial conditions. Then we simplified to get an expression for y of s. Then we used partial fraction decomposition to break down our expression and get a expression that looked like something that we could reference from our table. And then we took the inverse Laplace transform of each of the elements in y of s, these things right here, just going back from y of s to the input of the Laplace transform, got us y of t. If you have any comments or questions, or if I made a mistake somewhere, please let me know. This is the correct answer for this problem. I have double checked that. You all have a good day.